So can someone tell me what this represents? You may remember it from week 1. Anyone? Yes, there are clusters, but what the network represents in the real world? The internet, yes, this is the internet from a few decades ago, and this is a network model. So it's like a graph. We have nodes and edges. And these network models are useful whenever we want to model any sort of connectivity. If our data is based on interactions, based on pairwise relations. So some basics about networks. In networks or graphs, we have nodes and edges. So there are other names for nodes. Also, some people call them points, vertices, or agents. So this would be a node. This is node P. In social network, this node represents a social entity, for example, a person. Then we have edges, which are also called connections, lines, links, or ties, depending on the discipline. And an edge would be the connection between two nodes. Then there are different types of edges. So this edge that you see between nodes P and O is an undirected, unsigned, and unweighted edge. It's the simplest version of an edge. It doesn't have any signs, it doesn't have any weights, and it doesn't have any direction. So it's a bidirectional or a reciprocal edge. But we also have weighted edges. So if we have information on the intensity of the relationship between P and O, we would write it as the weight on the edge. So this could be intensity, this could be frequency. For example, sometimes these networks are used to represent co-behavior between people. So for example, person P and person O went to 5 meetings together. So we want to model how people interact in an organization, and these two people were present at the same time in 5 meetings. So then we represent it like this. We have signed or unsigned edges. So sometimes we want to represent positive and negative ties. For example, ties representing trust between people and ties representing distrust between people. Or if these nodes, if each of these nodes is, let's say, a country, we can have positive signs representing alliances, formal military alliances between countries, and negative ties representing wars between countries, or substantial, political disagreement between countries. So this edge that you see is signed. It's also directed. So you can see that there's a direction from P to O. So a directed edge is represents a relationship that is not necessarily reciprocal. It's one in one direction. Again, some terminology. So starting with degree, the degree of a node would be number of connections of a node. So for node I, we represent degree of node I with di. So in this example, the degree of this node is 0. It is not connected to any other nodes. The degree of this node is 1. The degree of this node is 4. So nodes that have a degree of 0 are called isolated nodes. And nodes that have a degree of 1 are called pendant nodes. Then the concept of connected component. So in this network that you see, 5 of the nodes are connected to each other, and there are 2 isolated nodes. So in total, this network has 3 connected components. So each of these isolated nodes, so for connected component, this is one connected component by itself. This thing is one connected component, and this is one connected component. So 3 connected components. So yeah, the word connected is about being connected to the rest of the entities in the same component. So you can also think of this as component. This network has 3 components. And the concept of component means being connected to the rest of the things in the same component. So each isolated node becomes a component by itself. And it is not connected to anything because it is isolated. Then clique is a complete graph. So for example, this is a clique of 4. A graph with 4 nodes where everything is connected to everything else. This is called K4, or a clique of 4. Clique of size 4, essentially. So in a network, we may have patterns that look like this. So maybe the whole network looks like this. In this network, which has 5 nodes, 4 of them that are in yellow form a clique of 4. So this clique would be a motif. A motif, it would be a pattern in a graph. For example, clique of a 4 would also be referred to as a motif. A clique of 3 looks like this. So let's say This would be a clique of 3. The triad is a clique of 3. So a triad is also a motif. So sometimes in analyzing a network, we look for these motifs. We look for these repeating patterns, right? So there could be multiple triads. And as we're going to see, sometimes using these motifs, using these repeated patterns in a network can be useful for speeding up an algorithm. Adjacency matrix is a matrix that shows the connectivity patterns of a network. So if in this network we enumerate the nodes like 0, 1, let me use a different color. If we enumerate them using right, I hope this is visible. 0, 1, 2, 3, 4, 5, 6. This graph can be represented also using an adjacency matrix that is 7 by 7. So in that adjacency matrix, in the first row, we have the connectivity patterns of node 0. So node 0 is, so there's no edge between node 0 and itself. Therefore, we write 0 in here. Then there's no edge between 0 and 1, so we write 0 in here, 0 in here. There's one edge between 0 and 2, so we have 1 in here, 1 in here. So it's a symmetric matrix. For an undirected graph, we get a symmetric matrix where each entry in location I and j represents the edge between I and j, represents whether there's an edge between I and j or not. So this row represents node 1, sorry, this column represents node 1, this column represents node 2. Same for these rows. So as you can see, this is not a very efficient way of representing this graph because we're repeating the same information in the upper triangle and lower triangle of the matrix. So can someone tell me what I should write here for this entry for 0 and 3? 1, yes, because there's an edge between 0 and 3. 0 and 4, there's no edge, so there would be a 0 here. 0 and 5, as you can see, there's an edge, so I have 1. 0 and 6, there's an edge, so I have 1. So this row represents the connectivity patterns of node 0. So from looking at this row, we can see that node 0 doesn't have an edge to itself. It doesn't have an edge to node 1. It has one edge to node 2, one edge to node 3, no edge to node 4, one edge to node 5, one edge to node 6. And looking at the first column, we see the same pattern. That's why this matrix is symmetric. So it would be 1, 1, 0, 1, 1. So I'm not going to complete the matrix, but I think you get the idea. All right, then a partition. So a partition would be a cluster, essentially. When we have a network, there are different ways to put some nodes into a group. That group is called a partition. So for this network, I may decide to put the nodes into these two groups. This is one cluster, and this is another cluster. And then this clustering into two groups is called a partition. So if the nodes are enumerated like this, if this is node 0, node 1, node 2, 3, 4, and 5, the partition that I just created in yellow can be shown like this, as a list of lists. 0, 1, and 2 are together. 3, 4, and 5 are together. So this is one partition of this network, one cluster, one clustering of the nodes in this network. Why we're doing this, you need to wait for the answer. So another name for partition is non-overlapping communities. So the two communities of this network are this community 1, or cluster 1, and community 2, based on this partitioning. And there's no overlap between them. There's no node that belongs to two communities. Yes?
Sorry, are communities that like a group of nodes containing cycles?
There's no special relationship about cycles in here.
Okay.
Yeah, this partition in particular, there's one cycle in each community, but I selected the partition arbitrarily. I could have I could have, yeah.
So partition is more like human defined. Not,
Yeah, yeah, yeah.
Not exactly that there's any relation in the graph itself.
We're going to make it a bit more clear
Okay.
why we partition a graph. But the partition you see on the slide is an arbitrary partition, which I just decided to put 0, 1, and 2 in one group, 3, 4, and 5 in one group. And then, if we have two partitions for the same network, there are some partition similarity measures that tells us how two partitions are similar or not. So here, one partition P1, is this. This is partition P1 in yellow, which involves two communities, C1 and C2. So for the same network, another partition would be P2. Let's say P2 puts 0 and 1 together, and then these ones together, 2, 3, 4, and 5 together. So P2 as a list of lists would be 0 and 1 in one list, and then 2, 3, 4, 5 together. Now, in order to quantify the similarity between partitions P1 and P2, there are three different methods: NMI, normalized mutual information; AMI, adjusted mutual information; and RMI, reduced mutual information. So just to give you an example, the AMI, which is a function, there's a Python code for it. AMI for P1 and P2 would be a value between 0 and 1, and the closer it is to 1, the more similar the two partitions are. So, for example, the AMI between these two partitions, I cannot, compute it without a code, but just to give you an example, this would be a value like 0.9. It's close to 1 because they are highly similar, except for the fact that they cluster node 2 differently. One of them puts 2 with 3, 4, and 5. The other puts 2 with 1 and 0. Except for that, they are the same. That's why this value is very close to 1. So a similarity measure for two partitions that are similar would be close to 1. A similarity measure for two partitions that are dissimilar, that are very different, would be close to 0. Questions? Technically, it's not exactly 0 to 1. In some situations, AMI can also take a very small negative number, something like minus 0.001. But the range is almost 0 to 1. Negative 1, no. Yeah. So for most partitions, for most pairs of partitions, the value of AMI is between 0 and 1. That's why we can think of it as some sort of percentage of similarity, as if these two are 90% similar to each other. So these similarity measures are not just about network clustering, but if you're solving a normal clustering problem, a problem that you would solve with k-means, and you find two different clusterings for the same data, and you want to see how similar the two solutions are, you can use the same measures: NMI, AMI, and RMI. NMI is the commonly used method. This has been around for maybe 20 years, and it has some issues. For example, NMI of two partitions become closer to 1 when they have more groups in them. That's why if we want to use NMI to assess the performance of an algorithm, this would be a measure that favors partitions into more groups. So if I just partition this network into 6 groups, each group with one node, the NMI between that and any other partition would be relatively high. That's why NMI is not the ideal choice. Still, many people use it in practice. If you read papers on clustering, probably you will see NMI. But it's better not to use it. So I just mentioned it so that you know what it is, but I don't recommend using NMI at all. I recommend using AMI or RMI. And for an applied data science project, this is a choice that you need to make because this is pretty much your performance measure for a clustering algorithm. So it is as if we have some old version of precision, which is problematic, and there's a new concept of precision which resolves that issue. So we should all use the better, improved version of precision. Otherwise, our assessment of what is going on would be impacted by the flaws of that old measure. Questions? All right, so we're still in the foundation of networks, so hopefully this will get a bit more interesting from the next slide. So you might have heard of network analysis or social network analysis. This is a topic that is from physics and sociology, but now has become, is being used in data science as well. So in social network analysis, we deal with networks that represent a social group. So each of these nodes would represent one person, or would represent one organization, or represent some social entity. And then there are different ways of analyzing a social network. So by social network, I don't mean social media or online social network. The concept of social network predates Facebook and online social networks by several decades. So one way of analyzing a social network is an egocentric analysis. This is where we focus on specific nodes. For example, you might have heard of centrality measures, which allow us to answer the question, which node in this social network is more important? Which node has more influence? Which node is more powerful? Which essentially means which person in this group has more influence, has more power. So these these terminologies actually come from social psychology. Then another perspective on analyzing a social network is looking at dyads. So dyads are two nodes and an edge between them. So sometimes we look at these dyads as the unit of analysis. The next level of analysis, the larger level of analysis, is a motif. For example, a triad is a motif, as I said. So this is a complete graph of size 3. And in our network, we may decide to look at triads, to look at essentially small groups of 3 people and how they are connected to each other. Another level of analysis is clusters, something that maybe makes more sense in data science. So if we have a network like this, we find these 5 groups and call them communities or clusters. So that's one of the main topics of discussion today, community detection. And then the largest level of analysis is analyzing the whole network. For example, you're comparing the power grid of Italy to the power grid of Spain to show that, for example, in Italy, the likelihood of power failure and blackouts is lower because of the connectivities between how the power is distributed in that country. So then in that context, we don't have a social network, we have an infrastructure network